Okay, well, good afternoon, everyone. Sorry I'm a couple of minutes late. Been having an issue with the internet, but we're going to get going with our conference on Chapter 9, which basically is an introduction to quantum mechanics. I just need to find out where I put my marker. There it is. Okay. So just to remind you, there's going to be another conference about half an hour after this one finishes, looking at gases. Okay, so I have a brief agenda here that I want to stick to. So let's get going with the Rutherford model of the atom. So this is a cartoon representation of the Rutherford model of the atom. I hope you can see that. So Ernest Rutherford, around 1910-ish, came up with this model of the atom. Basically, it's got two features in it. You have a positively charged nucleus containing positively charged protons, and you have negatively charged electrons outside of the nucleus. But there's a problem. So in the early 1900s, there was a problem. Why doesn't the electron collide with the nucleus? We know from Coulomb's law that the force between two charged objects is a constant times by the product of the charges divided by the reciprocal distance between them. So if we look at the Rutherford atom, we have a positive charge and a negative charge separated by, let's say, a distance r, which is this value here. So we know that the force, if we ignore the constant, it's proportional to the product of the charges. So here Q is charge, and the 2 just means I have 2 of them, divided by the reciprocal distance between them. Because the charges are opposite, we get a negative force. A negative force is an attractive force. So what that tells us is that if you take the Rutherford atom, over time, the negatively charged electron should collide with the nucleus, and you would have a zero-sized atom. So an analogy to think here would be water going down a plug hole. Water doesn't just go down the plug hole in a sink. It kind of goes round and round and round and round and then slowly down the plug hole. This would be analogous here. This is what we don't see. So because we don't see this, and that's our model, there's a disconnect between our model and reality in 1910. As this electron, if this electron did this, it would liberate energy because it would be losing energy. This is not what we observe. Because we don't observe this, our model doesn't represent reality. There's a problem with our model. This is not the only problem that led to the birth of quantum mechanics, but this was an important one in chemistry. Okay, I'm going to erase this board, and we're going to move on to look at the next atomic model, which rescued this model, which was Niels Bohr, the Bohr atomic model. So again, similar time. So around the time of the Titanic, around the time of Mary Poppins, all those iconic events. Someone called Niels Bohr was one of the fathers that led to the generation of this new type of mechanics called quantum mechanics. So he stabilized the Rutherford atom in a similar way to train tracks or planets orbiting the sun. It's called the planetary atom because the electrons now exist on orbits around the nucleus. So just as, you know, Earth doesn't smash into the sun because it's in an orbit, or a train doesn't smash into a building in downtown because it's on a track, these electrons are on tracks going around the nucleus. So the electrons orbit the nucleus. This stabilizes them. So this was a famed conclusion. He was able to represent the material world, at least back in 1910, by a simple adaptation stabilizing the atom. However, there were important consequences here. A consequence was that energy is discrete. What does discrete mean? It means it can only have certain values. So it means not continuous. Now, at the time, it was believed that energy was continuous. So it was believed prior to Bohr that the electron could go anywhere it liked, anywhere inside that atom. And every location would have a slightly different energy value, where all energy values were allowed, so the electron could go anywhere. Problem, it could go to the nucleus and lead to a zero-sized universe. If all the atoms become zero-sized, the material universe has no size, right? These orbits meant that the electron can be anywhere on that orbit. It can be anywhere on that orbit, but it can't be in between. The fact that there were energy levels that were not allowed, and only discrete energy levels that were allowed, is this idea of discrete energy. Another way of looking at this is that energy has quantities. And this idea of quantities of energy is where quantum mechanics came from. Quantum mechanics was developed after classical mechanics. It actually incorporates all of classical mechanics. You can't explain atoms successfully without it. And the birth of quantum mechanics was approximately around this time. And that's what was needed before chemistry could flourish. Okay, so you can pause this if you like or read around. I'm going to move on now to looking at how the Bohr model explains light phenomena. So the Bohr model of the atom explains light. Okay. Let's just look at a couple of orbits. let's call this one the n equals 1, this one the n equals 2, and this one the n equals 3. Let's just look at 3 orbits. Now, what we're going to do now, we're going to take a slice. We're going to take a slice and just focus on the slice. Okay, so we're just going to take a slice. But it's important to know that that's what we're looking at. We're looking at a slice of the atom. Okay. Here's the nucleus. This would be the radius of the atom or the size of the atom. It's known that visible light, or light in general, or radiation more properly, is the jiggling around, well, not all radiation, but radiation, most radiation is the jiggling around of electrons inside the atom. So Bohr was able to explain, for example, that if you have an electron here and it falls down here, then it loses energy. It loses the energy between the third level and the second level of the atom. Okay, these levels are called shells. So if an electron decays from the third shell to the second shell, there'd be a loss of energy. That energy would be a certain color of light. Indeed, the specific color of the light codes the energy value. So, and we'll look at the coding in a second, but different colors are different because they actually have different energies. So color, when your brain sees color, you're really looking at different energy values for light. Okay. So let's have a look. Let's see, in my notes, we're actually going to do a calculation. Okay, so let's actually calculate what color of light would be found if an electron decayed from the third level to the second level. Well, I'll need to erase this so we can do a quick calculation. So an electron is going to decay from the third level of the Bohr atom to the second level. We're going to use an equation. That energy is going to be a constant minus a constant, joules, that's the unit of energy, 1 divided by the final energy level squared, minus 1 over the initial energy level squared. Okay. This is going to allow us to calculate the energy difference. So I have my calculator on my phone. So that energy is going to be minus a constant now the final energy level was energy level 2, so it's 1 over 2 squared, which is 1 over 4. The initial level was 3, so it's 1 over 3 squared, which is 9. So it's best to do the bracket first, get that out of the way. Okay, so 1 over 4 minus 1 over 9. Okay, so this is 0.1389. So we're going to multiply that by this constant. Okay, so 2.18 exponent -18. Okay, actually, I need a positive value, so I'm actually going to get rid of, actually, it doesn't matter. Actually, it's probably best the way I've done it. So it's minus 3.03 by 10 to the negative 19 joules. So that's 3, and then 18, well, it's a point, and then 18 zeros, and then 3. So this is a very, very small number. Very, very small energy difference between the shells in an atom. The negative sign doesn't mean negative energy, it means a loss of energy or the emission of energy. So this amount of energy is lost by the atom. It enters your eye, and your brain tells you you've seen color. But what color is it? Okay. To show you that, I'll have to use this number but erase everything else. Okay. So we'll keep that number. We'll just erase the remainder of the question. I'm going to write this number up here. Okay. That's the, oh, that was 19, right? So remember, that was the energy from n equals 3 to n equals 2 decay. Notice it's one value, it's a discrete value, it's not a range of values. Around 1900, there was a guy called Max Planck. We're going to need his equation. He gave the world this equation. Energy is a constant called Planck's constant. And this is the symbol nu, it's a Greek letter nu, and it means frequency. Okay, so energy equals a constant multiplied by frequency, or energy is proportional to a frequency. So E equals h nu. We're going to use this equation here, and we're going to solve for nu. Okay, so this implies that nu equals E over h. Now notice I need absolute energy. So I'm just going to take the absolute value of this, which is just the positive version. Now Planck's constant, if you need it, it will be provided to you in an exam. I wouldn't expect a Chem 65 student to memorize Planck's constant. And to be honest, we might use it, but you really study it more in Chem 101. Okay, it's a very, very small number. 6.634 by 10 to the negative 34th power as units of joule seconds. So we can see that joule cancels joule, and we're left with 1 divided by second, which is a frequency, reciprocal time unit. Okay, so let's calculate the frequency. Okay, divided by 6.634. Okay, so we get a very large value here. Okay, so this is going to be 4.658 by 10 to the 14 reciprocal seconds. So second to the negative 1 means reciprocal second. A reciprocal second is also known as a hertz. So 1 over second equals hertz. That's an incredibly large number. So if you imagine the oscillation of a car engine around at rest, when you idle a car engine, about 2,000 revolutions per minute, and that sounds like brrr. Well, that's 10 to the 3. You imagine this, 10 to the 3. This is about 100 billion times more frequent than that. That's why you can't hear it. That's one of the reasons why you can't hear it. We're incredibly fast frequency. Okay, but it's hard to know anything about the energy here. Let's convert this to a color. Okay, my computer's just gone. Okay, there you go. So let's convert this to a color. Well, color is not based on frequency, it's based on the wavelength. So we're going to use a slightly different equation. So I'm going to keep this. I'll rewrite this at the top because I only have a very small whiteboard. Okay, so we know that the frequency is 4.658 by 10 to the 14 reciprocal seconds for N3 to N2. Okay. There's another equation we'll need. C equals lambda nu, where this basically is the velocity of light. C, it's called C because the velocity of light is a constant. Nu we know is frequency. And this is a Greek letter L. It's called lambda. And this is wavelength. This is basically the equation you saw in grade school. Speed is distance over time. If we look at the units, speed, velocity speed has units of meter per second. But we're just considering the units per second. Wavelength has units of meter, and frequency has units of 1/2. Okay. So speed is distance in meters divided by time. That's all that is. It's a grown-up version of a classical grade school equation. Okay, so let's solve for wavelength. Wavelength is C over nu. The speed of light will be given to you in my class. So it's 3, let's give a couple of decimals, by 10 to the 8 meter per second, divided by the frequency, which we calculated earlier. Okay. So we have 3 exponent to the 8 divided by, divided by 4.658 exponent to the 14. Okay, now we get a very small number, so 6.44 by 10 to the 1, 2, 3, 4, 5, 6 to the -7 meter. Reciprocal seconds cancels reciprocal second, and we're left with units of meter. Typically, when you look at a chart, it's converted to nanometers. So let's do a dimensional analysis. Remember, from your metric system, a nanometer is a billionth of a meter, or 10 to the -9 meter. So I know that a billion nanometer is equal to 1 meter. Okay. 10 to the 9 nanometer is 1 meter. Now I can put my meter input, 6.44 by 10 to the -7. So this is going to give me 644 with this one. So it's about 644 nanometer, which if you look in a textbook is red. You'll see a beam of red light. You can get other colors by looking at different transitions, but anyway, in short, Bohr was able to sell his idea. It stabilized the Rutherford atom, and also it explained light. Very, very successful. Is it the correct model of the atom by today's standards? No. Why? It accurately explains hydrogen. So this only explains hydrogen. It explains hydrogen very well. So what's unique about hydrogen? Well, how many electrons does hydrogen have? Hydrogen has 1 electron. So I can look at 1 electron unimpeded transitioning between orbits. What about more than 1 electron? Every other element has more than 1 electron. Electrons can interact. Electrons can transition. They can be impeded by proximity to other electrons. They can form pairs. None of this was explained by this basic, simple mathematics, and that's why more often than not, the Bohr atom just couldn't explain the complexity of all the other elements. Why is it useful? Because it's a vital pivot from classical mechanics to quantum mechanics in science in general, and specifically in chemistry. So I'm going to erase the board now, and we're going to summarize some of the relationships that we've seen so far, and they're vital moving forward in our course. And then we're going to transition into something that was an extension of this work. So I'm going to call this important relationships. There's 2 equations that we've looked at so far. We mentioned Planck's equation, E equals h nu. We mentioned this old grade school equation, C is lambda nu. If we combine those 2 together, for example, if I solve for nu, and then I insert nu over here, then I have E is h C over lambda. Okay. Where C over lambda is nu. Okay. This tells you something important. If you look at this equation and this equation, we know that energy is proportional to frequency. If we ignore the constant and make the equal sign a proportional to sign, energy is proportional to frequency because they're both numerators in the equation. This equation tells you that energy is proportional to 1 over wavelength. So energy is proportional to frequency, it's proportional to 1 over wavelength. Okay. I'm going to have to erase this. I'll move this up here, and then we'll draw a wave, and we'll try and rationalize that relationship. We said that energy is proportional to frequency. It's proportional to 1 over wavelength. Let's take a wave. So I tried my best. I didn't succeed, but I tried my best to keep it the same height. In fact, that's terrible. Let's try again. Let's bind ourselves within. So let's say there's a pipe. A wave can only exist in this pipe. This is the midsection of the pipe. So the height of the wave doesn't change, but it gets compressed here and it expands over here. Let's look at the distance between this point and this point. The wave repeats itself. It goes up, down, and it's ready to go up, down again. So that distance there is the wavelength. The wavelength is the unit of the wave. It's the smallest repeating unit of a wave. Here's another wavelength over here. Goes up, down, and it's ready to go up, down again. So this distance here is also another wavelength. Okay. You could say this is a short wavelength and this is a long wavelength. You have a short wavelength and a long wavelength. Frequency is the amount of waves per unit time. It has units of reciprocal second, so it's the amount of waves per unit time. This short wavelength would have a high frequency. So the frequency would be high if the wavelength is short. High frequency, short wavelength. If the wavelength is long, the frequency is low. If the wavelength is long and the frequency is low, then the energy is low. If the frequency is high and the wavelength is short, the energy is high. So we have low energy waves, high energy waves. An example of a low energy wave would be a radio wave or a microwave. We use radio waves to communicate, our Wi-Fi radio waves. We use microwaves on our cell phones to communicate. The skies are flooded with these waves, but because they're low energy, they don't do us any harm. If you could see these waves, it would blot out the sun. There's so many of them, but they're not doing us any harm. An example of a high energy wave would be gamma rays or X-rays or ultraviolet light, UV rays. We know that UV rays damage our skin. We know that X-rays can damage us. We want to minimize our exposure to them for medical reasons only. Gamma rays are also damaging. So these would be analogous to the longer waves, but they're more frequent and they have a shorter wavelength. So we're using our relationships to obtain a diagrammatic link to energy values. Okay, we have about 15 minutes or so left in this conference, so I don't know if anyone has any questions. I'll give you a minute. Well, I'll give a few seconds, see if anyone has a question. We definitely have some time. Okay, hearing no questions, I'm going to erase the board. And we're going to talk about something called wave-particle duality. So if you stick around till Chem 102, we'll be looking at this equation. So it's a couple of classes away. But we need to at least state it to eventually look at wave-particle duality. So this is arguably the most famous equation in the world, E equals mc squared. Energy is mass times by light speed squared. And there's another equation. P is momentum. This is the Newtonian idea of momentum. Momentum is mass times velocity. So an object with a mass traveling with a specific velocity will have a momentum. For example, if I hit the board, the mass of my hand, I impart a momentum. If I take the same mass, but I increase the velocity, there's a larger momentum. So we've all experienced this, you know, if you're playing tennis and you want the ball to move faster, you send the ball with more momentum. Okay. C is just light speed. So we've got velocity for light and then regular velocity. For the sake of argument, let's call all the C's V. So m v is the same as mc squared. Okay. We also have C equals lambda nu. Okay. This was our speed is distance by frequency that we saw earlier on. And yet another equation. Our Planck's equation. Okay, I think with hindsight, that's all our equations that we need now. Okay, we've got a smorgasbord of equations. Let's set this E equal to that E so that this equals that. Okay. So all we've done, we've set these two energy equations equal to each other. Okay. Now let's replace nu with this. Remember, we know that nu is C over lambda. So this is H nu, where nu is C over lambda. I think we agreed we're going to call CV. C is just a special type of velocity, so let's call it V. Okay, let's go ahead and change that to V here. Save confusion later. Okay. And we said that MV is just P, right? Momentum. Okay. So we can see we have a velocity on both sides. So we can cancel those. So we just have momentum equals h, Planck's constant, over wavelength. Or we can write wavelength equals Planck's constant over momentum. Remember, momentum is mass times velocity. Let's just spell that out. This is possibly the most useful form in terms of teaching and pointing out what's going on. We have an equation with a wave on one side of the equal sign and a mass on the other side of the equal sign. Well, the wavelength is typically used for waves, and mass is typically used for particles or objects. But we've got one equation that has both. This is known as the Broglie equation. We have one equation with both variables in. Roy equation. And this is what led to something called wave-particle duality. What does wave-particle duality mean? It means that particles that are affected by quantum mechanics, so typically anything within an atom is affected by quantum mechanics. Atoms themselves and things inside them are affected by quantum mechanics. Whereas we are used to thinking of them as particles, we actually have to consider them as wave particles because they are described by wave mechanics and particulate mechanics. Duality means at the same time. So, well worth knowing that equation. Okay, so we're going to erase this. Okay. Let's quickly calculate the wavelength of an electron. So we've got wavelength is h over mv. Now h, remember, is 6.634 by 10 negative 34 joule seconds. The mass of the electron you would be provided with if you need to know. But it's around 9 by 10 to the negative 31 kilograms. And the velocity of the electron, electrons have a mass, so they have to move slower than the speed of light. So for argument's sake, let's say it's around 10% of the speed of light. Okay. So 10% of the speed of light is 3 to the 8 meter per second. So 3 to the 7. So let's say that's okay. Now you may or may not recall, or you may not know that a joule is a kilogram meter squared per second squared. Okay. So we can rewrite joule as meter, so don't forget the S. We can rewrite joule as kilogram meter squared per second squared. The kilogram cancels the kilogram. You have second to the negative 2, that's a denominator. And here you have a denominator that's already a reciprocal second, so that becomes a second. So in short, that second and that second are going to cancel those two. Okay. And that meter is going to cancel one of them. So the only unit that survives is meter. So we have wavelength in units of meter. Okay, let's see what that number is. Okay. Let's see what that number is. We have 6.634 exponent 34 to the negative divided by 9 exponent 31 to the negative divided by 3 exponent to the positive 7. Okay. So this wavelength is around 2.46 by 10 to the negative 11 meter. Okay. Now, in quantum mechanics, we wouldn't necessarily, I wouldn't expect you to know this, but if I can ask that you take it from me, forget the unit, any value that's larger than this value sorry, any value that's much larger than this value, we would have to consider quantum mechanics. Any value that's smaller than this, we would ignore quantum mechanics. You just use classical mechanics. This would be the wavelength. Okay. Let's look at the wavelength of a human. So yes, we're made of atoms, we're made of subatomic particles, we have a wavelength. So again, real quick, because this is larger than Planck's constant, 10 to the negative 11 is larger than 10 to the negative 34, we have to consider wave-particle duality for electrons. We have to consider the mass of the electron, but also the wavelength and frequency of the electron. And now I just ask that you accept them. Let's look at the wavelength of a human. So the wavelength is 6.63, 4 by 10 negative 34. We use the same units, so joule seconds, so second, kilogram, meter squared per second squared. The mass of a human, I'll use myself as the representative human. I am about 70 kilo. Much heavier than an electron, thank goodness. About 70 kilogram. I definitely can't move a tenth of the speed of light. I would say, if an Olympic sprinter can run maybe 20 miles an hour, I'll say I can run 10 miles an hour. So 10 miles per hour. Let's just quickly, rather than do a long dimensional analysis, let's just say I can do 7 meters per second. I don't know, that's pretty average. Actually, that's pretty fast. Let's say 5 meters per second. Okay. The units will all cancel. As before, we're left with meter. So let's have a look. Let's meet the answer. By 70. Okay. 1.90 by 10 to the negative 36 meter. Again, with the electron, 10 to the negative 11 was much larger than Planck's constant, so we have to consider the wave nature as well as the particle nature. For something as large as me, though, I get a wavelength much smaller. Heavy objects have smaller wavelengths, if you'll recall, because wavelength is proportional to 1 over mass. So the more massive you are, the smaller your wavelength is. My wavelength is smaller than this value. When that happens, you can pretty much ignore the wave nature of the object. So that's why I don't look like a wave to you. I look like a particulate object. I'm dominated by particles. Not true for electrons. Okay. We have a couple more minutes. Let's see if I have anything. Okay, in the last few minutes, I think I'll just erase and summarize the important take-home messages from this first quantum mechanics, or intro to quantum mechanics conference. Okay. So in summary, we know that energy is proportional to frequency, which is proportional to 1 over wavelength. We can add this proportional to mass. Know those relationships. Energy is proportional to frequency, proportional to 1 over the wavelength, proportional to mass. If the wavelength of any object is greater than Planck's constant, you must consider as a wave particle. Quantum mechanics. Like we just saw with the electron. Remember, this is 10 to the negative 34. If the wavelength of the object that you calculate with the de Broglie equation is greater than 10 to the negative 34, you must consider the object as a wave particle according to wave-particle duality. So it's a wave and a particle at the same time. And that's the realm of quantum mechanics, the realm of discrete energy. This applies to electrons. We as chemists study electrons. So chemistry really is quantum mechanics. Don't tell anyone. If the wavelength is less than Planck's constant, you need only consider the object as a particle. We calculated my wavelength. It was smaller than Planck's constant. I manifest myself as a particulate object. Nobody would look at me and see a wave. This is just basic classical mechanics. Classical mechanics is continuous energy. Remember, Rutherford thought that the electron could go anywhere, any energy value. Quantum mechanics, remember, was discrete energy. Remember, Bohr said, oh no, Rutherford, the electron can only go at discrete locations. It can transition between them, but that's a discrete transition, and it's a discrete energy value. Okay, so that's about the top of the hour or top of the half hour, which when we started. So that will conclude this conference.